Okay, continuing on this problem, which in fact, remember, is already rotated 30 degrees here. So that's a 30-degree rotation. So we've done our coordinate system. We've defined, and I want to point out here how important this step is of sketching in your reactions as single unit vectors. So reaction A in the Y, reaction A in the X, and a reaction B in the Y. That may help some of you to realize what you're doing is you're going to calculate what is the torque of this vector, the torque of that vector, and it's going to have to be reacted to by an equal and opposite torque or spin from that vector. Since if you pick your point of rotation to start here, that's why you put your coordinate system there, that this torque has to equal that torque. And you'll get a vision then, even within the mathematics of rotation, with a positive and negative moment, you'll get a vision of whether or not you're going in the right sense. So if you notice here, I wrote the reason why you put the coordinate system there is you don't have to sketch out these radial vectors, but these radial vectors are there. So for instance, the radial vector from here is just 0 to 0 to 0, 0. The radial vector to the reaction force here is the full distance between the supports, 13.41, and that comma 1 is incorrect. It should be 0 because there is no change because we've rotated our coordinate system. The force in the reaction in Y, the reaction at A, it's an A there, A, let's see, A in the Y, is 1 up. So you have it 0, 1, and the force over B and Y is 1 up. And now, again, I've changed, based on this interface, you start to learn to use your interfaces because the rollover tooltips doesn't work for me because every time I move around it goes away. I've just changed my quick props there. And so I can pull that over here, hopefully move it around a little bit. And in that, you can see that the radial vector to my force vector here is at 10 and minus 2. So I'm going to go ahead and write out 10, comma, minus 10.19. Remember, this was the two vectors that I added together by moving them to a concurrent force. And then my force vector is equal to minus 2.76, comma, minus 8.4. Now remember, when you write these up, right, you can do your calculation. We're going to do that over here in a second. But I do want to point out, and I'll leave this Wolfram alpha around a while, just so you can do it. That's just a vector cross multiplication, and you want to learn. You can do it in this Wolfram alpha in a 2x2. Though many 3D engines want to give it a three unit, three coordinate description. But in this program, we can say cross. We're just going to teach you the syntax and the fact that screen real estate starts to be, and a calculator helps you with screen real estate basically, because you can do the calculator on the side. This is 10, comma, minus 10.19, comma, minus 2.76, comma, minus 8.4, close hard brackets, and then in this case you hit a return, and in Mathematica you got to go with a shift return. Kind of interesting as different programs treat the return differently even. So as you go here, you're going to go ahead and hit a return, and you'll see what we get. Now I'm going to have to scroll down through that to give you the answer here. Oh, there it is. There's your input. There's your resultant, and it didn't like it. So let's see what we did wrong. We can go to Mathematica form, and we can see the Mathematica plain text. It did not want to necessarily do that cross product because my format looks right. So let's go ahead and see what happens if we do cross a little bit differently. Let's see what happens when we put a 0 in there. And you should be able to do a cross product of a 2 by 2. So we're not certain that this is the program, not certain anything. Cross one vector and another vector. Hit an equal sign. And in this case, it did give me an answer. So this, like SketchUp, it needs a 3 by 3. So, but we end up with an answer of minus 112. So the moment of that force about A is minus 112. Now, really, you should want to start being able to do this as well, but let me go ahead and write that minus 112. So the reaction here, so right here, this R cross F of the resultant of the external forces is equal to minus 112.24. And of course it is 24K. So the reaction at B in this, so the reaction, the moment R to B, in other words this, times F at B has to be equal to a plus 112.24, which just means all you've got to do is got to take the 112.24 and divide it by 13.41. So jumping around here, we don't want to use Wolfram for that kind of stuff. 112.24 divided by what turned out to be 13.41. And you get an answer of 8.37. So the reaction at B equals 8.37, or we hope. And what you do right away is you draw and grow up that vector, grow that vector up to be what it's supposed to be, 8.37. Now if you go back to here, you see how close that is to this reaction force here, this delta Y on their force. So we'll see whether my drafting is correct and a number of other things once we get through here. So we have the reaction at B is 8.37. Realistically, within that, if we grab, double click, if you right click on the properties, if you can all of a sudden be pretty good about going right click properties on some of these blocks, you can put these extra factors in there, which I do not have. You can actually add a dynamic block information, which I don't have set up in this drawing, probably because I'm in an old version. So I'm going to hit cancel here, close that there. I'm not going to close that block reference around. So I'm just kind of showing you too much, I presume. But I want you to realize that in reality, this problem is probably in the end best solved by doing force orthogonal distance or comparing circles. So I'm going to do that right now. Circle from the insertion point of my block over here, or 0, 0, perpendicular to that line. That's one circle. And the other circle, if you notice, this is oh so close, regen. That other circle basically is that 13.41. So when I list this, it's a ratio 12.67.96, and it's going to be a little bit, the reaction force is going to be a little bit less because it's farther away. So I can go over here and say 12, it's a little bit less, so you're going to go the 12.70, 68, divided by the 13.41, and multiply that by the magnitude of the force, not the x or the y, just the magnitude. So I'm going to list the magnitude of the force, and the magnitude of that force is 8.84. So you're going to take 8.84 times that last answer, and you get a reaction of 8.37. 0.36, which essentially, if you see here, is maybe even a little bit better because of the fact you see that we have the same number here. So the reaction turns out to be the same way. Now, where that may get odd is doing the other reaction. So we'll go and do that next. Thanks for listening.